Have you ever stopped to think about what your doctor really sees when they look into your eyes? I mean, it's way more than just a vision check, reading letters off a chart. They're actually exploring this incredible hidden world, a complex landscape with its own geography. And today, we're going to pull back the curtain on that secret map.
So let's start with a question. That clear part on the very front of your eye, is it a perfectly smooth sphere? You'd probably think so, right? But the truth is, it's way more complex. It actually has its own unique set of peaks and valleys, almost like a fingerprint for your eye.
And get this, that unique landscape can be mapped. So today, we're diving into how doctors create and, more importantly, read these incredibly detailed maps of your eye. And understanding this hidden geography is absolutely crucial for everything from planning surgeries like LASIK to catching diseases early enough to save your sight.
All right, so where exactly is this map located? Well, it's all about the cornea. Think of it as the crystal clear window at the very front of your eye.
The cornea basically has two huge jobs. First, it's a tough, protective shield for all the delicate stuff inside your eye. And second, it acts as the eye's most powerful lens. It does most of the heavy lifting when it comes to bending light to help you focus. So for you to see clearly, this little window has to have just the right shape and just the right strength.
And that leads us to a really critical question. How does a doctor know for sure if this window is structurally sound? How can they tell if it's safe to perform a vision-correcting surgery or if there's some kind of hidden weakness lurking beneath the surface? You can't just look at it, no, you've got to measure it.
And the very first, most fundamental measurement is its thickness. This brings us to our first key technology, a cool-sounding word, pachymetry.
Pachymetry is, simply put, the process of measuring how thick the cornea is. Now, this might sound like just one little number, but it is incredibly important. A cornea that's too thin can be a big risk factor for complications in surgery, and it's also linked to a higher risk for things like glaucoma progression.
So, how thick are we talking about here? The scale is just mind-blowing. An average, healthy cornea is only about 530 microns thick. That's just over half a millimeter. To put that in perspective, that's about the thickness of 5 human hairs stacked on top of each other. We are measuring something incredibly delicate.
And to get a measurement that precise, doctors use some seriously amazing tech. It started with ultrasound probes that actually had to touch the eye. But now, it's evolved into these sophisticated, non-contact methods that use light and advanced cameras to create these super high-resolution thickness maps without ever touching the eye's surface. Pretty cool, huh?
Okay, but thickness is really just one piece of the puzzle. To truly get the whole picture of the cornea structure, we need a map. And this brings us to the crucial difference between seeing in 2D versus seeing in 3D.
So first up is topography. I want you to think of a topographer like a geographer who's charting the elevation of a mountain range. It meticulously measures the curve of the front surface of the cornea, showing you exactly where it's steeper and where it's flatter, and it creates this beautiful color-coded map of just that surface.
But then you have tomography, and this takes things a giant leap forward. If topography is the geographer, tomography is the architect. It doesn't just map the front surface, it creates a complete three-dimensional blueprint of the entire cornea. We're talking the front surface, the back surface, and the thickness at every single point in between.
So let's just nail down this key difference. Topography gives you a 2D surface map of the front. Tomography, on the other hand, provides a 3D volume map of the entire structure. And this ability to see not just the front, but also the back surface and the thickness at every point, well, that's a total game changer for diagnosing some really complex conditions.
So why does this 3D view matter so much? Let's look at a real-world example where these maps become literal sight-saving tools, spotting a disease called keratoconus.
Keratoconus is a condition where the cornea starts to thin out and get progressively weaker. And over time, the normal everyday pressure inside the eye causes this weakened area to start bulging outwards, forming a sort of cone shape. And, as you can probably imagine, that cone shape dramatically distorts your vision.
Now, this is where those maps become absolutely indispensable. A 2D topographer might spot some steepening on the front surface, but a 3D tomographer sees all the signs. It can pinpoint the exact spot where the cornea is thinning. And here's the revolutionary part. It can detect bulging on the back surface of the cornea. That subtle change is often the very first sign of trouble, a critical warning that a 2D map would completely miss.
And in a progressive disease like this, one that gets worse over time, catching it early isn't just important, it's everything. Finding that tiny bulge on the back surface, way before it becomes a major problem on the front, can make all the difference in preserving a patient's sight and, frankly, preventing a surgery that could make things a whole lot worse.
Because when you find it that early, you can actually treat it. There's a procedure called corneal cross-linking that uses UV light and vitamin drops to strengthen the cornea, and it effectively halts the disease in its tracks. So that early detection, all thanks to these advanced 3D maps, leads directly to sight-saving intervention.
It's a pretty incredible progression when you think about it, isn't it? From a simple thickness measurement to a full-on 3D blueprint that lets us stop a disease right in its tracks. It kind of leaves you with one last question. What other secrets are hidden inside our bodies, just waiting to be revealed once we learn how to see not just the surface, but the entire structure in 3D?